Bam. Section 1.2, we'll discuss what are number systems. Because, okay, in algebra, you're trying to find what's the right number that solves an equation, but what do you mean by number? Depends upon what kind of problems you're trying to solve. There are several number systems. Sort of the earliest one is called the counting numbers. It's just all the whole numbers at least equal to 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, up to 20, up to 100, up to onwards forever. Now this dot, 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 that denotes infinity, which is a unproven and perhaps an unprovable assumption. So there's a little bit of mysticism here, I gotta admit. Also, we don't include the number 0, but we do include the symbol 0 as part of Hindu Arabic notation, which between you and me, I think is sort of like, it was an evolutionary leap on the equivalent, about as good as printing or the wheel or maybe fire. It's not that new and that old an invention, only from the 1400s, but can you imagine trying to build a computer, say, or a space probe or a car using Roman numerals? Insane, impossible. So we're not only a few centuries away from something that's, I think, has made us into a new species, but not aside from that. Now, given two counting numbers, oh, and these are denoted n. This is n written in kind of gnarly font called Fraktur from the German, because in the 19th century, it was the Germans who did a lot of scholarly work about mathematics, and so they got naming rights. Anyhow, thing about n, the counting numbers, is that given two numbers in it, there's sums in it and their product is in it. If a and b are in n, and so is a plus b and a times b. We say that n is closed under times and plus. You can't get outside of by adding and subtracting. So basically, n is great for problems which involve adding and subtracting, but it's not closed under minus and divide. 1 minus 2 is -1, which is not in the counting numbers. 1 over 2 is 0.5, again, not in the counting numbers. All right, so there came a point where someone said, you know, we really need numbers less than 0, or whole numbers less than 0. So we gave a name to that, z, the integers, which are the whole numbers signed, including 0. So 0, 1, 2, 3, 4, etc. -1, -2, -3, -4, etc. Here we put a dot, dot, dot on both ends. So it's mystically infinite in two directions. Now, okay, this word z is, again, from the German. It means Zahlen, or whole numbers. Okay, it's closed under plus, minus, and times. You can add, subtract, and multiply whole numbers and get a whole number. But not necessarily divide. 1 over 2 is still is 0.5, which is not in z either. Let's see. Oh, by the way, a question for you. What are these numbers less than 0 called? What are they called?
Negative numbers.
Negative. Well, what does that word negative mean, other than for numbers? I mean, aside from math, what does the word negative mean? Well, it means to deny.
Less than value of 0.
What's that? Less than or less below 0. That's mathematics. But prior to this using it for this, negative means to deny. So a negative attitude. Can you go to Warp Speed, Ensign? Negative, Captain. That sort of thing. And the reason why we call these the denied numbers is at first they didn't believe it. We need these numbers for math, but I don't believe them. So they called them an insulting name. You'll see that again later on. Let me ask you something. How can you have, let's say, -3 apples? How would that happen? Anyone willing to guess? What?
You took away 3 apples?
Yeah, you owe somebody 3 apples, right? So you owe someone 3 apples, and the first 3 apples you then get, you'll immediately lose because you got to give it to someone else. So tell me something. So negative in this sense means a debt. And so, of course, it took the introduction of modern banking into Europe before they finally decided to believe it. All right. Now, also you can think of negative numbers as backwards motion. Going forward 2 steps is +2. Going backwards 2 steps is -2. Okay, closed under plus, minus, and times. Well, what about divide? 1/2 is 0.5. It's a fraction. It's not a whole number. It's not an counting number, and it's not an integer. It's a quotient. So we'll call that set of numbers Q, the quotients. Also called the rational numbers because these are ratios between integers. They're of the form n divided by m, where n and m are integers, but except for m not equal to 0. We dividing by 0 gets you infinite or indefinite quantities, and that's a problem. So we generally avoid that. I will discuss them later, however. All right, and here, if we start listing them, we'd have to draw a line, and then 0, 1, -1, and then halfway between is half and -half, and you have the quarters, 3/4, -1/4, -3/4. Here are the eighths, and then there's thirds, fifths, and so on. So we're dividing the continuous lineup into fragments. So here we're getting numbers between numbers. Q, the quotients, is closed under plus, minus, times, and divide. This is known as a number field. It seems to have a certain kind of completeness. And okay, it seemed to be good enough to work. So okay, here's what we have. And the counting numbers is a subset of Z, the integers, is a subset of Q, the quotients. All right. And as you expand it, you get more kinds of numbers, but it's a little more, there's more crowding, and in some sense, fewer rules. Now, if you take a rational number and you expand it into decimals, it'll eventually repeat. 1/3 is 0.333333, etc. We denote that 0.3 with a line right above the repeating block. 17/99 is 0.171717, repeating forever. We denote that by 0.17 with a line over the repeating 17 block. 8/45 is 0.17777. So here, just the 7 repeats, and this 1 just appears once. So we note that as 0.17 with a line over the 7, and not over the 1. You have to be very careful between distinguishing this and this. Watch out for typographical errors. Most of my students' errors are typographical. Now, or here's, let's see, 641,495 divided by 990,000 comes out to 0.642137137. The 137 repeats after a little bit of non-repeating. So 0.642137, borrow that repeat. So every rational number has an eventual repeating rational decimal expression. But it's easy enough to write a decimal expression that doesn't eventually settle into a repeat. 0.1, 01, 001, 3 zeros 1, 4 zeros 1, and so on forever. Here it never repeats because these blocks of zeros get longer and longer and longer. Or here's one, 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you just count out all the integers in the decimal expansion, and it never repeats. So these are not ratios of whole numbers. So they're called irrational. This is another case of mathematicians giving some perfectly innocuous mathematical concept an insulting name because they're a bit scared of it. So here's some famous irrationals. Really, honest to God, they made themselves into history. You start with a square with side 1, right angle here, and look at the diagonal D of a square. All right. This is denoted the square root of 2. Later on, we'll see why. Basically, if you take this and multiply it by itself, you get 2. So square root of 2. You can approximate it as 1.414 to 13562, and on and on and on, but it never settles into a repeating pattern. Now, there's a group of mathematicians way back when who discovered something called, who followed a guy named Pythagoras, who, believe it or not, ran a mathematical cult. They all sorts of weird stories about Pythagoras. Anyhow, he posited that, he said, basically, he believed that all numbers were of this form, were quotients, and all lengths were of this form, quotients, and so on. He was wrong. So when he discovered that this number, which is right there, a perfectly reasonable line, length, is not a ratio of integers, they really went crazy about it. Honest to goodness. They made it a cult secret. One of them threatened to threaten the others that he was going to tell the world, and they threw him off a ship. Weird stuff. I mean, I don't approve, but I guess I do sort of approve of people taking that seriously. And yeah, so that's the square root of 2, a real famous one. Or here's, how about this? Given a circle with a diagonal with a diameter d, and c is the distance around, called the circumference. Then c divided by d is a number we nowadays call pi, which is the Greek letter p. And this is approximately 3.14159 to 6535, and so on forever. Again, not a ratio of integers. Let's see now. 3.14159 to 6535 8979 323 846 264 33 83279 502 88. Obviously, I had way too much time for myself when after that. Okay, it's a famous number, and there's a sort of a ritual nowadays of calculating pi out to billions of digits in order to test how well a computer works. Here's more. This has been known for thousands of years. This has been is a little bit known only for a few centuries, but it's a biggie. E. It's the limit as n goes to infinity of 1 plus 1 over n to the nth power. Or E is also 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3 plus 1 over 1 times 2 times 3 times 4 plus and so on forever. Okay, and it's also approximately 2.71828182845 and so on, never repeating. This is a big important number. It's used in banking and physics and biology. Basically, anywhere there's some kind of exponential growth going on, E will show up. It turns out that E and pi have some curious connections. We'll see more about that later. So since not all integers, not all numbers, not all lengths in the line, and not all decimal expansions are ratios of integers, we have to talk about R, the real numbers, which are all such lines and lengths and ratios of decimal expansions. Actually, there's two ways of looking at R. R is a set of decimal expansions. So 3.14159 and so on. Can also be thought of as a set of lengths of lines. So here's a line, and here's 0 to 1 with length 1, and we move over here to a point here, pi distant units along. So there's this is a digital concept of the real numbers. This is an analog concept. Here we talk about counting and arithmetic. Here we talk about measuring and geometry. And the identity of the two does a great deal of heavy lifting in mathematics. Now, R is closed in addition, subtraction, multiplication, division, and what are called convergent limits. And it's nested subsets. The counting numbers are a subset of the integers, which are a subset of the rationals, which are a subset of the reals. There are other number systems going further. We will get to, I think we'll get to C, the complex numbers, which includes square root of -1. And instead of forming a line of numbers, it forms a number plane. And even beyond, I think we'll be getting to C sometime this semester. We will not be getting to H, called the quaternions. This includes 3 square roots of -1 with some weird qualities where I times j is not the same as j times I. It turned out to be useful in 3D computer graphics. You can do rotations and translations of objects very easily using the quaternions. And it won't get you something called gimbal lock, which is which other ways of describing things in space can have a problem with. So if you get into computer graphics, you'll probably be introduced to quaternions. Okay.
Excuse me, Professor?
Yes.
I'm not sure of the format that you're using here. Are we supposed to be grasping what you're going over? Is this just an overview, or can you kind of tell me? I apologize to interrupt you, but you're going over a lot of material.
Yeah,
I don't know if
sections a night. This is how it is, and we'll be I mean, since it's available on Canvas, you can review it later on, and I'll be posting these Zoom sessions also at the base of the on the Canvas page, so you can review that later on. Or if you miss a class, you can review it. This is the basic description. Well, basically, I'm describing what's in the section. I hope that helps.
Okay. Yeah. Thank you.
No problem. Now, the real numbers fit onto a line. Here's a line called the real number line. That's no surprise. And therefore, you can put it into a left to right order. You have two numbers on the number line. Here's A and here's B. You can say that A is less than B, or that B is greater than A. It's basically left to right. So for example, -7, -1, 1, and 7. 1 is less than 7, that makes sense. -1 is less than 1, that makes sense. -7 is less than -1. Oh, it's a bigger number, but it's to the left of it. One way to think about it is, put it this way, which would you rather be, $7 in debt or $1 in debt? Which?
$1.
So therefore, -1 is bigger than -7, and -7 is less than -1. And of course, -7 is less than 7 because you'd rather have 7 in credit than 7 in debt. Now, this -7 is in some sense bigger in size than -1, although it's to its left. Robert Heinlein, the science fiction writer, said that a guy who's $1 million in debt, he drinks champagne that night, but the poor fool who's $1 in debt has to tighten his belt. So there's not just debt and credit, but immensity of debt or credit. So therefore, we talk about the absolute value. We write that, denote that by writing this two parallel lines around number x. That's basically x with a positive sign, or how far x is from 0. So the absolute value of 1 is 1, absolute value of -1 is 1, absolute value of 7 is 7, absolute value of -7 is 7. So -7 is 7 away from 0. And the absolute value of 0 is 0 because it's at 0. So now some examples. Compare -9 to -8. Is it less than, greater than, or equal? Yeah.
It's less than.
Yeah, less than, because you would rather not be -9 versus $9 in debt versus $8. So yeah, 3/5 compares how to 0.06. Well, okay, first, let's write 3/5 as 0.6. How's that compared to 0.06? Less than, greater than, or equal?
0.06 is greater than 0.6 is greater than 0.06.
That is correct. 3/5 is greater than 0.06. You'd rather have 60 cents than 6 cents. -11/5 compares how to -0.73. -11/15. Okay, well, first we expand -11/15 as -0.73333333. -0.73 is -0.730000. Now, all right, careful now. Less than or greater than?
Less than.
Less than, because I mean, this is a bigger absolute value than this is on account of the 3's versus the 0's, because they're both negative, so that reverses order. So yes, this is less than this, like here. Now let's try this. Evaluate the absolute value of -5.9. What's that?
5.9.
5.9. The opposite, negative, of the absolute value of 5.9. What's that?
-5.9.
There you go. Now careful. The opposite of the absolute value of -6. What'll that be?
-6.
-6. First, here the absolute value makes this negative sign go away like that. And the absolute value, the negative of that is -6.
Oh.
The absolute value of -a is the same as the absolute value of a. Well, okay, that covers our first two sections. I mean, I'm going to go on. The next section will be, about signed numbers, how to add, subtract, multiply, and divide numbers with plus and minus. I mean, we'll get to that tomorrow. In the meantime, however, let us end this. Stop recording.